Hello everyone, we're continuing our conversation on chemical kinetics. And in the previous lecture previous video, we looked at what are the things that we can change to affect the rate. And one of them was the concentration of our reactants. And the question might have arose that why does changing the concentration of the reactants actually affect the rate? And okay, well, maybe that's an obvious answer, is because your reactants, they need to react to form the product. But inherently, well, there is some kind of reaction mechanism, right? So there are bonds that need to break and again form in some particular order for the products to form and hence for the reaction to proceed. And that dictates the reaction rate. So there is some order in which things need to happen, and eventually that will lead to how quickly things will happen, depending on how these things happen, right? And if we were to increase the number of molecules, in other words, if we increase the reactant concentration, that will dictate the rate. And one thing now that we can write down to assist us in looking at the how the concentration influences the rate of a chemical reaction, we will see is called the rate equation or the rate law, and that is connected to the concentration of species. So now that's a term you haven't heard before. So what is a rate equation or a rate law? So you know that we can determine what the effect of the concentration, given that we keep the temperature held constant, if we say, for example, vary the concentration. So let's set up an experiment where we say we vary the concentration of our reactants, all right, so we vary the concentration of our reactants in order to see how our rate responds. So that's basically what we're going to do now. So that's what you need to imagine. So what will happen if we vary the concentration of our reactants? How will the rate respond? And that is what happens in the graph here below. So in this case, we increase the concentration of the reactant N2O5. So it's just an example reaction. You've seen the decomposition of N2O5 before, and its concentration was doubled. And for example, so its initial concentration went from 0.5 to 1 molar. And what do you notice about the average rate? The average rate also doubled. So that tells us that the doubling, so in other words, the initial concentration of the reactant was doubled and the rate also doubled. So what that then tells us is that there must be some proportionality between the rate of our reaction and the concentration of our reactants. And we write that down mathematically using this symbol to say the rate of our reaction is proportional to the concentration of our reacting species. So for the general reaction, A gives B plus C, you can say that the rate is proportional to the concentration of the reactant A. Okay, so that's what you see happens. Now, anytime in mathematics have an expression, oh, that's the wrong thing. Anytime in mathematics where you have a situation where you say rate or something is proportional to something else, to get to a point where you then can say rate equals that thing, you must introduce a constant. And the constant that we are going to introduce, the proportionality constant, so in this case, we then call the rate constant. All right. You can further remember that the rate of a reaction is always equal to minus the change in the concentration divided by the change in time. So I hope you followed thus far. We just basically said what will happen if you increase the concentration. We see you proportionally increase the rate of the reaction. And if we see there's a proportional relationship between the rate and the concentration, that means we can then write an equation by introducing a constant. And this constant, well, it should have a name. We give it the name, the rate constant. All right. And this thing now, in the form that it is where it says rate equals to K times the concentration, is what we call a rate law. So when you have something of rate equals K, so a constant multiplied by the concentration, it is a rate law or a rate equation. So that is what a rate law is. It is an equation by which you can actually calculate the rate of a chemical reaction. Okay, so let's look a bit more general into that. So let's say you have a general reaction where you have some stoichiometry, so alpha A plus beta B gives chi X. So that's, remember, the alpha and the beta are just stoichiometric coefficients. Then it means this rate or this reaction has a rate equation of the form rate equals to K, the rate constant, multiplied by the concentration of the reactant A to the power M, multiplied by the concentration of the reactant B to the power N. And you will notice that we now introduced some powers here, powers M and N, or exponents M and M. And the reason we did that is because we don't necessarily know if the rate here is proportional to, so meaning here where we said it's proportional to, is it to the power 1, is it to the power 2, is it to the power 3, is it to the power 4? So what your M and your N does is it just says we need to solve to know whether or not it's A squared, A cubed, A to the power 4, B squared, B to the power 3, etc. Right? That's something we will solve, and it's something we will look at a bit later on. Okay. Importantly, it is not your stoichiometric coefficients. So if you look at your rate equation, it is not the stoichiometric coefficients alpha and beta. Okay, so those numbers are not the same as M and N. They are not the same number. All right, so that's what a rate equation is. Your rate equation is something where you can calculate rate equals your, where's my pen? There's my pen. Where you write your reactants, concentration, and you raise them to the power something, and you have a rate constant. Okay, that's a rate equation. And that's the idea of this video, that you gather the rate is proportional to the reactant concentrations, and to be able to say equal to them, we introduce something called a rate constant. All right. Interesting fact, just the last thing that I'll note here, is because your catalysts are not written as reactants, you do not include them ever in the rate equations unless they are homogeneous catalysts. So meaning if they are in the same phase as the reactants, then only can they appear in the rate equation. But in general, we will indicate that to you if that is necessary. So you will in general know what to include in the rate equation. Like here, A plus B, then you know what must go in the rate equation. All right, that's the broad introduction to rate equations. Cool, I'll see you in the next video where we look at the idea of reaction order, or the order of a reaction.